May need to get you a speaker of some sort. Um, so how is everything going? Yeah, I know it's bad programming from STEM plan, right? We That's one of the reasons that it's been a challenge here, but hopefully, like I say, that they can respond to your email or something with an easier way to deal with this. But okay, so you have it already. All right, yeah, we can put that somewhere on Microsoft OneDrive so that we can access it. Um, and we can start playing with the uh, AI or something. Maybe tomorrow we'll have time. Yeah. So let's talk some more, I guess, about the different projects that we've got going on here and how we'll get you involved. What I've sort of got planned for you for the next couple of months here. We've got some projects for Diamondback and in the petrophysics space. So this is one of the clients that I've been working with for about 5 years now, maybe a little bit more. Uh, they are a mid-sized independent operator, about $50 billion market cap. So they're comparable to Occidental, or a company like that. And they've only got two petrophysicists working with them right now. They're very lean, very cost sensitive operator. And they've hired a third guy that'll be starting probably in April, mid-April to late April. But he's going to be new, so he'll require quite a bit of training to get up to speed. So the way that the company operates, they've had a restructuring recently. Typically, they give us projects to work that are sort of focused. Like there's so many wells that need to be interpreted or edited or whatever, and then we just do that and then turn over the petrophysical analysis back to them. We've got a workflow that I sort of developed that the company uses with all of the software tools that I have, and we'll get your IP set up quickly here so that you can do that. It might not be a bad opportunity to start with this one project that we've got right now. I'll get Pond and Ploy to help you with that. But the basis of it, a lot of the work that we do, right, is just cleaning up data and doing interpretation. So they have a 3D seismic survey. It's called Flying Dutchman is the name of it. Let me see. Hold on a second here. Let me start my IP. It crashed. I'll share my screen here in a second. Thank you. Yeah, it's in various states. So the problem with Diamondback historically has been they have grown as a company in size through acquisitions. So they buy other companies. And when they buy the companies, they get the data that the other companies had, right? And we've got a pretty long history there of buying all these different things. So they started back probably to 2021 by purchasing a fairly big set of companies. They got QEP, which operated in the Permian Basin and operates up in the DJ Basin up in Colorado. And when they bought QEP, they didn't bring much of the staff over. They basically fired everyone, right? And yeah, the QEP folks had a fairly decent sized petrophysics team. So I'll just share my screen here. They had a big database that they built, that they did interpretations in, and the way that they did it is sort of not very good, but it's okay. Like they got porosity and saturation kind of correct, but some of the other things were off by a bit. And how they depth shifted data, how they edited data wasn't the best, but it's not like you're starting from scratch, right? Like they've got curves that have been renamed. You can find things, we just have to kind of take that data and pretend that it's raw and start. But let me give you a sort of grand view of things, right? Here's North America, right? And then here's the Permian Basin in West Texas that we're working in. And I've got some overlays on here with faults and stuff like that. But the general bit that you're going to be spending a lot of time in is this outline here. This is the Midland Basin. So let me do some drawing here. Easier to draw than it is anything else. So like this thing here, right, is a basin, Midland Basin. This thing over here is the Central Basin Platform. So this is deep, right? This is shallow. It shallows up, and this is mostly carbonate over on this platform. So we've got this survey. The survey outline kind of looks like this. Inside the southwestern portion of the Midland Basin, and the geophysics team is doing a, hold on. They're doing a post-stack quantitative inversion using the data from the well logs to help tie their low frequency model. And the geophysicist that's working this, he uses a piece of software called Hampson Russell. And he needs to have data that's a pretty good quality or condition in order to do his well ties and to condition the seismic model. So in order to do that for a post stack, we need to have good bulk density and compressional sonic data. So all these blue dots are wells that we have inside of that survey outline, but some of these wells are missing data. Some of them don't have the appropriate types of data that we need. So we're not going to be looking at all of them. At the moment, I think a whole bunch of these have been gone through. Like I'll just pull one up and show you really quickly here. Like this is some well in that area. And this is a sort of displays that we look at. So starting from the left, we have the tops. So these are the formations that exist in the Permian, and I'll get you a stratigraphic column so that you can start to figure out what these are. But to give you an idea, this is a computed mineralogy tract here. So, starting from left to right in that mineralogy tract, you have the gray stuff, that's clay. The yellow stuff is sand, quartz, and then the blue stuff is limestone. So starting from the very top up here, this is basically the full Permian section that you'll see. There's these formations on the top that are called the Grayburg and the San Andres. And these are typically, like you see here, there's either a bunch of dolomite or limestone, and then there could be a little bit of quartz that comes and goes, but these are primarily carbonates. And then, these things are, you can see just by the porosity track here where my mouse is, you have like 15% porosity in some of these, could be higher. And, they were, or they still are production targets in some parts of the basin, but these were like conventional reservoirs that have been, drained for, 70, 80 years now, right? So at this point, basically they're used for disposal. They inject water into them from all the frack jobs and stuff, right? They frack all these wells, they produce all this frack water and produced water from the formations, and they inject it into these water disposal wells. And that's typically kind of where it's going, is the Grayburg, San Andres. Could be going a little bit shallower as well in some of the conventional bits. And as you move through down into the next formation, this is the Glorieta. So this thing is kind of like a sandstone, and it's typically pretty low resistivity because it's wet. It's got a high quartz content. It still has some clay in it as well, but it's pretty conventional. Again, you can look at the porosities. There's 10 to 15%, and this thing really isn't a production target because it's so wet, and it's sort of very lean on hydrocarbon, right? But it's there. So like, when you interpret these things, just be aware that, these two intervals up here are kind of a carbonate model. And then we use, a particular sort of setup for calculating the properties in the Glorieta, because it's deposited so proximal and so quickly that there isn't much ability for, the generation of like TOC, organic material. So that's one of the big inputs that we put into our petrophysics model that affects the porosity computation, is TOC. And basically the way that it works is, the petrophysics inversion is trying to separate the mineral matrix and the porosity volume, right? Two separate things. And where it gets confused is TOC, because TOC sort of acts like a porosity filling material because it's very low density, right? It's just like a bunch of little carbons and a couple of hydrogens, depending on how old it is and how compacted it is, how mature they say, right? The thermal maturity and all this stuff. So if we put TOC in the model here, it's going to clobber the porosity. It's going to reduce it by quite a bit. So we've got like a way where we zero out the TOC in these upper intervals, so you don't have any, so it computes the correct porosity. And then the next formation after that is the Clear Fork. And so this thing is like a mess of siliclastics, usually pretty high clay content. We're looking at 30 to 40% clay here. And then there's carbonates that come and go, right, through the depositional system. And you can see that on the mineralogy. And this has TOC in it. It has quite a bit of TOC in it. So we put the TOC in the model there. The next formation is the Sprayberry. It's the upper Sprayberry is what they call it. And this is a Permian age formation. Typically, you can see it in some areas of the basin where it has a lot of limestone in it, but it's typically a sand. It's a silt, right? So pretty high permeability for an unconventional, like microdarcy type of perm. It's not super tight, it'll flow fluids, but it's typically pretty wet. And we are Diamondback, I say we, most of the operators in the Permian Basin are drilling horizontal wells in that interval. So it's just one of those things, right, where you produce a lot of water, but you produce oil with it. So there's opportunities to make development wells that are economic, but you have to deal with all of the produced water. And that's the story of the Permian Basin at this point in its lifetime, because it's a mature basin, right? It's sort of like the Gulf of Thailand in many ways, right? People have been producing wells there for a very long time. So, you just have to deal with that water production, and you're still making oil, but you got to deal with the water. The middle Sprayberry, they call it, which is below the upper, that is more of a shalier, player rich type formation. There's some silts developed in it as well, and it's also a target. They drill horizontal wells in it. And then below that is the Joe Mill formation. And the Joe Mill is sort of a layered system of, they call it a hybrid. And you've got some well-developed sands in there, depending on where you're at. Typically wells that are up here in Martin and Howard County, like where this outline is for this other seismic survey. These things are more proximal to source, so they have a lot more sand, higher quality sands. This particular well doesn't, right? You don't see really well-developed sands in here. It's kind of more like a just siliclastic shale, right? 20% clay, maybe not that great, 8 or 9% porosity. But this could be a big producer in a lot of areas. One of the things that I've been talking about for a long time with Diamondback that they just haven't really picked up on is, the way that these operators work, in particular Diamondback, is that, as I mentioned, they're cost sensitive. They're trying to reduce costs through operations. So, what they did originally back in like 2010, so about 16 years ago, they started drilling the first horizontal unconventional wells. Like when I was out there and I was drilling all these things, we would pump, pretty good quality proppant. And part of the reason for that was, we had people who were getting on this, industry experts, a lot of good frac people. And, they were telling the operators what to do, and they were telling them to do it the right way, like let's pump the right size sand and get the right kind of fold of increase, right? Get the right kind of fracture conductivity that we need for these things to flow. And then people started realizing, well, if I have to buy white sand from, Wisconsin in the United States, which is far away, and I have to pay to transport it, it's expensive. So it's cutting in on my profits. So operators like Diamondback, what they do is they source their own proppant. They mine their own sand locally, and it's a brown sand, right? It's feldspathic. It's got all these different minerals in it that are kind of like lower crush strength. So when you frack wells with this, first of all, they're using 100 mesh, which is small sand. And then second, that sand doesn't really stand up very good to high stresses, right? Closure stress from the geomechanics bit, right? So it crushes. And the problem is when you frack really low permeability intervals, you get away with it, right? Because the fracture does not need a lot of conductivity to flow because the reservoir can't flow at high rates, right? But the Sprayberry and the Joe Mill in particular, and potentially the Dean, which is down here, these are sort of like the hybrids, right? There's silt beds in there and sand beds that could be microdarcy or millidarcy permeability, but they're interlayered with all these really tight shales. And what people have been doing is they're just pumping the same frac with the same shitty sand on everything. And the results could be a lot better, I think, if they were to actually engineer and design their completions to put bigger sand in some of these intervals, right? So moving from there, you have the lower Sprayberry. So you've got the upper, middle, and then lower. The lower Sprayberry is a shale. So organic rich. Usually, this one here has got a lot of carbonate material in it, but this is much lower porosity and permeability. Now we're in the nanodarcies, right? 200 to 300 probably. And this thing is a pretty good target, right? They drill a lot of horizontal wells in it, makes a lot of oil. And, it's just tight. The Dean is sort of the siltier thing. Like I mentioned, it's kind of wet. So some parts of the Dean, you have a lot of good oil in it. Some parts are really wet. You just have to deal with the water production. But it's a little bit finer grained than the Joe Mill, right? Then after you get through that, there's all this Wolfcamp stuff. So Wolfcamp A, B, C, and D. And the Wolfcamp was the original targets that started the whole unconventional thing in the US. So like when the Permian Basin started drilling the very first horizontal wells back in 2010, this is all that we developed. We just drilled wells in the Wolfcamp, Wolfcamp A's, Wolfcamp B's, Wolfcamp D's. The C generally is not a target. In parts of the basin, like here, it's a tight carbonate. In other parts of the basin, it's really high clay content, and it's a gray shale. There's not a lot of organic material in it, and it doesn't produce very well at all. But the D, in a lot of parts of the basin, this was a poor quality target. They went after it really hard back in like 2012. And it's a Pennsylvanian aged rock. They called it the Klein, but they drilled the hell out of it and put the wrong kind of completions on it, and it didn't work. So everybody kind of abandoned it, right? They said this is not a good place to drill. Don't bother anymore. And when I was at Apache, what we were doing there, we had a completions engineering manager that was an idiot, and she wouldn't listen to us. She thought the best frac to put on this was a hybrid frac, which, you know, if you looked at those at all, the way that a hybrid works is that you pump a slick water pad and you pump, you know, this low viscosity fluid to generate geometry, and then you switch over, you know, you set up your operation so that you got a hydration unit and a blender to work with cross-linked borate gel, bore-based gel. And you switch over to like a linear gel system to start transporting proppant, then you cross-link it. And we're talking about like 15 to 20 pound, maybe 25-pound cross-link gel that they start pumping in. And it was just not working because of the trade-off between surface area and conductivity. This rock is so tight, it doesn't need, you know, high conductivity and large proppant. And the only reason that you pump the gel is so that you can transport that proppant at high concentrations, right? So they screwed this up because they put the wrong frac on it. They should have been fracking it with slick water at low proppant concentrations, and it would have worked. In 2025, Diamondback and a lot of other operators came back to the Wolfcamp D and started drilling wells in it and putting slick water fracs on it, and it's working now, right? So everybody's all excited because they've got Wolfcamp D wells again. The stuff below that, you get into the Strawn, which is typically non-prospective. There's a lot of garbage rock in here. It calculates a porosity, but it's very tight, and there's not a lot of pay. And then below that is this really high clay interval. It's called the Chester, and they break it up into like Chester A, B, C. And the Chester is like just garbage rock. There's nothing there, and it's very chemically unstable with the drilling fluids that they use. So they're using a water-based mud that's like 9 pound per gallon, just cut with whatever slop they have in brine. And the clay reacts very strongly with that, and the wells tend to wash out and break out really badly. So you get really poor quality data over this interval, and there's not much there to get. Below this, which I don't have logs for in this well, but I'll see if I can find one here, is the Barnett Shale. And that is what Diamondback is really, really interested in right now. They've opened up a whole bunch of inventory. It's a new target, sort of. We tried to drill a lot of Barnett Shale wells in the past. I was part of a bunch of exploration projects where we went in and drilled these things, and we did it wrong every time. Like we drilled the wells in the wrong areas with like really super high stresses. We put the wrong kind of fracs on it. And we even cored a couple of these things, and the rock looked so bad. Like it was just the wrong area. I'll give you another example. I just told you that the Lower Spraberry Shale is a great producer, right? Tons of well inventory there. at Apache, we looked at this thing, we're looking at the petrophysics, and I was saying, man, we should be drilling a well in that lower Spraberry. Nobody wanted to do it. And we fought with management, they refused to drill one, and we finally got them to drill a well. But they drilled it in the wrong area. They drilled it way up here, and it didn't work. So they said, see, look, you petrophysicists are idiots. You don't know what you're talking about. If they would have drilled a well in the basin, it would have worked, right? We just got unlucky. And that's exactly what happened with the Barnett. People were drilling wells down here in Upton County and over on the platform and in the Delaware Basin over here, and they weren't working. But once people started drilling wells like in Martin County and Midland County, Occidental in 2025 started publishing results from their wells, and people were, getting really excited, like, damn, we need to be drilling that. So this is typically what that section looks like, right? You've got a caliper curve here in red. You can see what's happening, right? And this is the bulk density correction curve also. So this thing is just washed out really bad, right? 14-inch hole. And they drilled it with probably a 7 7/8 inch bit. So, really, really bad. And then you get into the Barnett. So the resistivity goes up. There's organic material here, and there's some interbedded silts and stuff. You can kind of see that. And then you also have this thing called the Merrimack, which is right below the Barnett, which has some fairly good quality rock. So they're landing wells like right here. They're fracking, I think, down into this stuff. And they're potentially even fracking into the Woodford Shale, which is a high organic source rock that sort of feeds a lot of these systems, right? A lot of oil is generated here. And it kind of, through buoyancy or whatever, it fills up these reservoirs. These are making wells. So the problem is they want to do all this analytical work and mapping and stuff to figure out, where to drill Barnett wells, but look at the data quality. It's really bad. So we have a hard time. That's something that we're going to be working on this year, I'm sure, is cleaning up this Barnett interval using machine learning and all kinds of different stuff to get that to where, we can trust the data to be able to interpret it. And then below the Woodford is the Devonian. So these are really old rocks now, right? Devonian age. They're deep. You can see what the depths look like. Usually it's, 10, 11,000 feet or deeper. And the Devonian itself, you can see the porosity track. Like there's some stringers of porosity in this thing. You will find it. It can have oil in it. It's typically a chert mixed with the limestone. So all this yellow stuff is chert. Like this thing at the bottom here, this might be a decent little interval if you had a vertical well, you just pump a couple of or pop a couple of perforations in this thing and frack it or something, right? Or even just perforate it and put a small acid job or completion on it, it might work, right? And this thing rings really hard on seismic too because of the impedance differences, because you're coming out of these really soft shales into this really hard chert, right? And limestone. And then below that, you've got like all these other things, the Fusselman and the Montoya, the Ellenberger, which are dolomite and carbonates, very old, right? And very tight usually. But the Ellenberger itself, because it's pretty well-developed dolomite, has got quite a bit of permeability. So they usually use that thing as a water disposal target as well, right? They'll drill specific saltwater disposal wells down into the Ellenberger and just pump as much water as they can down them. That's become a problem recently because of induced seismicity. So, if you haven't been paying attention to what's going on in Texas, they've been getting like magnitude 5, 5.5 earthquakes, right? From all this water that they're injecting down deep, and they're causing faults to slip and stuff, right? So anyways, the state of Texas issues saltwater disposal well permits. And the permits come with, you have to permit the well, they'll approve it or deny it. And with the permit usually comes like volume or injection rate criteria, right? You can only dispose of so many barrels per day at or certain rates or whatever. They're sort of like turning down all the permit applications now for the Ellenbergers. So people are turning back to these shallower formations to inject stuff into because they can't inject it deep. And there's a lower risk of induced seismicity by injecting into the shallow sections. But we're still getting earthquakes. And we're still seeing like visible deformation at surface even using like satellites and stuff. They're seeing the ground is actually coming up, right? You're pumping enough shit down there that you're causing like centimeters or more of the ground elevation to change from all this water. Yeah, we've got earthquakes. I mean, there's these websites, right? Like you can go to these things, right? And look at this is all water disposal shit over here in the Delaware Basin, all of these things. I guarantee it. So there's, 1.2, 2.2s, there's threes and fours. You can filter by, let's do 4+, right? So you can see when these things happened 3 weeks ago or whatever, here you got a 5.4 magnitude earthquake that happened on May 4th, 2025. That was a year ago. There's one in Midland that was a year ago. It was the 4.8. There's a 4.3, 4.3 2 months ago, January 26th. Right. So these are big enough. They're shaking people's houses and cracking the walls and stuff, similar to the earthquake that we had in Bangkok. So, anyways, big thing now. A lot of work to do there as well at Diamondback if you're interested in that sort of stuff. But that's the general lay of the land. What these wells will look like is you'll see stuff like this, right, where you've got mixed match data from different runs, and we can't really do much with this. We can't interpret it. See if I can find another one. Some of it we can, right? This isn't terrible. Some of the wells will be just raw data like this, where somebody loaded a last file that they got with these different curves in it. Right, you got a gamma ray there. You've got everything you need to do a petrophysical interpretation: sonic data, resistivity, bulk density, PE, neutron porosity. Right, so we're good to go. But the other thing to note too is look at the depth range. This is all very shallow, and yeah, and when you go above the San Andres and the Grayburg formations, you get into this. It's like the evaporite series that they have there. So this is a lot of salt and hydrite, halite, and sylvite and stuff like that. So, it really isn't very useful to us to bother about trying to fix this stuff. Usually also because it's salt. What happens when you drill it, right? It just washes out. So not good data. And you'll see a lot of these wells in here, like I say, look at all these dots, right? But a lot of them are just shallow salt wells and stuff that we can't interpret. This is a good one. But you have to be careful too, where this has got an H on it. So this is a horizontal well that they collected data from. And really, we don't know if this was a horizontal well where they drilled a pilot first and then they collected the data and then they came back and did a sidetrack, or if this is the actual data from like a horizontal section, or if it's like if there's a curve building through this. Like we need to find deviation data to figure out what the hell's going on. So here's your deviation curve. You can see what that looks like. So it's vertical basically until you get down here, and then it goes to 90 degrees. So this whole bottom section is we can't really interpret that because it's deviated. But let's see what the tops look like. Yeah, we don't even have tops in this well. So I don't know who did the interpretation for this, but it doesn't look very good. Another salt well. This one, you've got some data, but it's only here at the very bottom. So it looks like they, they drilled the well down deep and they just logged that very bottom piece of it, right? That's where you're, oh no, never mind. So you do have they log neutron all the way up through the casing, but you only have open hole logs down here. In the Devonian, this is below that Woodford Shale. And I know this is the Woodford Shale because it's always got really super high gamma rays. So if I scale this to 500, you'll see you've got 600 there. And this whole thing is like 300 or more units, right? So that's the Woodford. This is the Devonian. They must have been looking at the Devonian for some reason. They thought there were some conventional porosity streaks in there. Let me see if I can find another well for you with calibration data as well. So you may be asking the question or wondering, like, how do we know that our model is correct, right? Like, how do we know that our porosity computations are right or if they're wrong, stuff like that. And in some cases, go ahead. Yeah, so sometimes we have core. That's great. Like in this case, we have core points, right? It's got the C on the well, means that there's core in it. So you can see like, I don't know if this is whole core or rotary sidewall cores, but somebody cut these cores and we kind of did that. But really, higher resolution measurements are coming from things like NMR. So here's a good example of that. This is that Barnett section that I was talking about, right? So you can see like up here in the Chester, the NMR porosity is usually a really good, accurate measurement of total porosity coming from the wireline tool, right? And the black dash curve is the NMR porosity and the red curve is what's coming from our model. Now, I'm not too worried about this mismatch up here because the hole is washed out. I know that this Chester suffers from chemical instability and everything. So trying to match this, and it says that there's 40% porosity. So, if you go to the books, maybe when you were in university, right, they teach you that there's something called a critical porosity, maximum porosity for rocks. So, you're already approaching that. These are completely unreasonable values for porosity. But once you get into the, if you look at just that density correction curve, you can kind of see like right here, the hole condition starts to improve. And that's when our model starts to match, right? So we've got a pretty good match. Now, there are sections where like what's going on down here, right? This is that Devonian. Remember I said there's conventional streaks here. There could be a couple of lobes of porosity that our model just isn't picking up for some reason. But for the unconventionals, we did a pretty good job. This is another well that's got NMR and a bunch of core plugs. So here you can see too, like I've got porosity points. And this is typically what you see, right? You've got a lot of scatter. So using core to calibrate your logs is difficult sometimes because of all that scatter, You don't know exactly where the plugs were selected, and the logs, the tools themselves are averaging the data over a large vertical section. So they may not match all of these spikes, right? But the NMR tool, starting all the way up here in the clear core, is already matching pretty well, and then in Sprayberry, it matches well, right? So our model, we've got TOC measurements here. Like our model's balancing everything. It's getting the grain density right and our porosities right. As we come into like the Joe Mill, it's pretty accurate, right? Lower Sprayberry, pretty accurate. And you can see like, all these core plugs. You see the scatter there, right? Like, I'm sure that these clay numbers are probably correct, just that our logging tools can't read that finally. So I don't try to force the calibration to the core. I try to force the calibration to the porosity. If I get that right, then it doesn't matter, That's something like, quantifying all that stuff. I don't know that a lot of work has been done there. Like getting actual numbers, like what's the percentage? We have tools to do that. So like I've got this little program, it's called error analysis. I'll show you how that works real quick. So if you come into this thing, you can add curve pairs of two curves that you want to compare with each other to see what that error is. Like, how much error do I have? Mean absolute error, whatever. I don't know why this thing froze, but I guess it's because there's so many wells here. Got it. Yeah. So we'll do, I'm going to get rid of all of these wells except for that one. We had that Brenda Dorcas thing. I can find it in here. It's easier sometimes if you just do this, if you kill this thing. And I'm gonna close all these other wells that we're not messing with because they're just noise. They're not helping us. No. An IP is pretty slow, so. All right, so these wells now, it should go really quickly. And these all have NMR. So you could do this curve pair thing, and then we could say, we're gonna look at the predicted curve, which is the mineral solver total porosity from our inversion. And then we're gonna look at the NMR curve. So, all right, one of the wells didn't pass. Which one was it? The DUSEC. Okay, good to go. So now this thing is showing you the differences between the absolute error for these wells, right? Between the total porosity computation. So some of these are pretty bad. And the reason for it is because the data that we're putting in hasn't been cleaned up necessarily, right? Like some of this NMR data is bad too. Like this stuff down here or whatever, it could be washed out, right? Where I've got values of like 20 or 30%, that's wrong, But you can go in here and sort of look at the analysis, like which zones got the worst rankings, bias, negative or positive bias. And it shows you here, like I've got one well, for example, it's got a pile of error in the lower Sprayberry Shale. This is at KD 4476. So if you come into this and you look at it, you'll see why the NMR curve went to -9 or whatever, right? In that upper section. So that's why it's an artifact, right? It's not real. And you can look at error versus depth. Here again, it's scaling it. So let's do like 0.5 or something. That should be even less, 0.2. So you can kind of see like the shallow sections are bad. We've got that one bad section there and that one well. Everything else is not so bad, right? You see it by well. Do comparisons by well too, right? Mean absolute error or whatever. But these are the sorts of tools that I've been building software for to work inside of IP. These are custom programs, right? That we wrote ourselves to do this sort of analysis, to answer these questions, Then what's acceptable? I think you should be within one porosity unit because the total porosity in a lot of these intervals is like 8%. So that's 15 to 15, 10 to 15% error is what I would consider acceptable. Anything higher than that, I've set that to 10%. And that's mean absolute error as well. So really we should set that down to that 0.01 that I was talking about. Then all of a sudden, like bam, everything is lit up, right? So even 0.05, I think you're gonna see that it's pretty bad in a lot of areas. But the model, you're not gonna be able to get it much better than that. We've done a lot of work on it. It's good. It's predictable. It's generalized. It works well in a lot of different places with a lot of different types of data. So I'm happy with it. Been doing a good job. So that's how we kind of calibrate these things. Obviously, we make here like this stuff here, you know, the NMR tool was turned off probably when they logged it up to the shallow section. And then you can see even in here, I've got these washouts and I've got, you know, 50% porosity, stuff like that. You would need to edit that, clean that up. So one way that you can do that, I'll just show you really quickly here because we're just kind of fucking around anyways. You can make a cross plot. Easiest way to do that actually is like this. So I can see that, you know, I've got like this 1-to-1 line here, and then I've got all this bad data scattered, right? So I can actually just like create a polygon or whatever around this. Say this is my good data. I can create a curve. I'll call it XP, total porosity. And I'll add that to the plot also. So the way IP works is it creates this flag and it's showing up here in this track. And it's equal to a null value wherever the data is outside of that polygon, and it's equal to 1 wherever it's inside of the polygon. So what I have to do then is run a user formula where I can say if XPP4 is less than 0, then I set it to 0, or then I set it to 1, otherwise I set it to 0. And what that's doing is anywhere it's null, it sets the bad hole flag to 1, otherwise it's 0. So I run that. So now I should have a flag in here. I'll put it in this track. Wherever the data is bad, this should be equal to 1, right? And it's 0 everywhere else. So now I could come into my machine learning app and say, okay, I want to create a new total porosity curve using, actually, what well am I in? I'm in the Pegasus Field Unit 3 well, right? So I'll do it over everything. I will use all of my quad combo data that I think is good to do that with. And I'll give it that curve, total porosity curve. And then for the flag, I'm going to give it that XPP4 flag curve, right? And I'll use, this is Microsoft's ML.NET that I programmed up in here. So you've got different types of decision tree-based regressors and other things. I normally just use like XGBoost, like GBM, right? Gradient boosted decision tree. And we can train the model. So what did I do wrong here? XT4 flag. So you can specify. Yeah, I'll show you what it does. Like, so you have a training fraction here, right? It does a split, 80% training, 20% for validation. And this is what it came up with. So like I've got, you know, PFI where it'll show you the permutation feature importance on there. It'll show you cross-validation data, and it'll show you the training versus predicted data sets, and then kind of what it did. So we don't have the best R squared in the world here. You can see that the mean absolute error is like 0.01. So it's more than 1 porosity unit, right? Is the error on our model. But, you know, this is one realization where it randomly sort of changes a lot of the hyperparameters on these runs. So I can run this for longer and see what it does. The other problem is we have to be careful. Generally, the AutoML thing from Microsoft does a pretty good job on not overfitting, but sometimes you can end up with overfit data. But suppose that we're good there, right? So now I can swap out this DT curve for the one that I just created, which I believe is going to be called T4 underscore MLNet. So that red curve now is the fixed total porosity after the regression, right? So you can see like in all the washouts, it's back to normal kind of. And then if I put my mineral solver porosity back in there, and I'll make this like blue or something, I guess. You can see it basically overlays the corrected total porosity curve from the NMR. There's some places where it's different, and that's because still we have these bad washouts, right? Like maybe I need to fix it in here. But for the most part, looks pretty accurate now, right? So if we went back to this now, and we said I wanted to look at my predicted curve from that set, which is going to be this P4 MLNet, and then I'm going to put my mineral solver total porosity in here. Now we'll just do it for that one well. Now I can see how much error I have, right? Like it's not looking as bad. 2%. Still, right? Like you've got some of these intervals, not so much in the Sprayberry and the stuff below, but once you get into the wolf camp, it gets a little bit bad, you know? And that's down in here where you get rid of the other curves. It's too hard to see all these things. I'll just put this here. So the black curve now is the mineral solver porosity. So you've got areas like here where, no, I've got significant difference, 5% units, right? Even down here, I'm off by 2% units, you know. But it looks a hell of a lot better than it did before. And then when you look at it by zone, you know, these upper zones we don't care about because these are all these salts and stuff. But there's your mean absolute error over the producing intervals. And it's all below, you know, 2%. Some of these are about 1%, right? Yeah, it gets better, right? You can like, we can redo that too, where you don't select all the tops. You don't want to look at all that garbage, right? We can. So I think we have to put that curve back in there. Right? I thought I had a thing in here where I could select the tops. I guess not. Oh yeah, I can. I can select over here. So you just select the tops that we're interested in. Not even the strong, really. Wolf camp A, B, C, D. So now I'm not looking at all that garbage. There's your mean absolute error by zone, right? And you can see the bias where it's over predicting and under predicting, depending on where you're at. So my predicted curve is under in a lot of the wolf camp, and it's over in the middle Sprayberry and the Joe Mill. So useful stuff, you know. So what we'll do tomorrow is get you set up with IP, get it running, and we'll get you working on the AI stuff for the frac project, and then we'll get you working on this Flying Dutchman survey and all these wells that need to be worked up, and you'll have all these tools at your disposal. And by the way, if you're interested, I'll spend the time with you anytime we can figure out when to do it. But there's like an API basically that they set up with this, and you can run like Jupyter Notebook, and you can run stuff in Python, write your own code to do whatever in the petrophysics software. So. If you think of stuff you want to do with the data or whatever, I've got a lot of problems. I'll go through with you. Maybe next week. I don't know. We'll try to do it this week, but like I have some pretty interesting challenges that I think uh, would be worth trying to solve. Like we've got some pretty high impact things to look at that I just don't have the time to play with. And one of them is depth shifting data. So what we're trying to do, like I'm writing my own petrophysics software and stuff, and we're trying to write these different modules and IP and things to make it easier for all of us to interpret the data. Like, and one of the biggest things that you're going to find when you're starting out with some of these wells, when you start working them, we have to depth shift the data because it's off depth, and we do this by hand. It's very time consuming. If you think about the total sort of time that it takes to do a well interpretation, I spend about 70% of my time depth shifting the data, and the other 30% is spent like editing and normalizing and doing the petrophysics, right? So, I've been thinking for a long time about automating that process, and I've tried a lot of different things. There's been a lot of focus from the industry, but nobody's solved this problem yet, to my knowledge. And I'll go through it with you, right? Like we can look at how a human does it, and then try to see if we can get the computer to approximate that. But there's lots of algorithms, dynamic time warping, these signal processing things to try to align data. But every attempt that I've made at it has failed. The computer just cannot understand what needs to be done. And part of the problem is that we have to deal with both negative and positive polarity in the alignment of the curves. Because if you think about it, the most simple example is density and resistivity or something, or resistivity and gamma ray. Okay. You have two different things that can happen that have different polarities. Number one, I have low gamma ray, clean, limestone, right? But it's tight. So very high resistivity. So you got low gamma ray, high resistivity. I could also have a sandstone, low gamma ray, but it's full of water, right? Low resistivity. So I've got low gamma ray, low resistivity. I got low gamma ray, high resistivity. Which one is it? The computer doesn't know. You know because you're smart, right? You're a human. And you say, well, this is a sandstone and it's full of water, so duh, but the computer doesn't, it can't figure it out. All it says is I got a spike, I need to align it. And what it does is it tries to align the high resistivity up here down with the low gamma ray or something, right? And it doesn't want to put these together. And I've tried all kinds of different approaches, like flipping these things, but this is a really challenging project with super high impact. Just to think about, not that you need to make it a focus of what you're doing, but and the other thing, just to start thinking about now also, is one of the things I did with the Pond employee is I sort of forced them to do a presentation at one of the local chapter meetings for the professional organizations based on the work that they did during their internship. So I'd like to do the same with you. We could either try to do it at an SPE meeting in Bangkok or at the SPWA meeting, but start thinking about over the next few weeks, what it is that you're really interested in, so that we can get you, we'll get you a data set to work with from someone that we can do some really interesting, meaningful work with, that has we could publish a paper or something with. It's not just that you're wasting your time, right? That you're you're actually doing something relevant. And yeah, well, it's a different world that we live in, right? As you can probably tell already, there's lots of work, right? It comes very quickly. And for consulting business, uh, really, typically consulting shops are always old guys, like you work for a company for a long time and you learn at the company, and then you go to consult when you've got 20 years of experience. It's like you can't consult with 1 year of experience. Nobody's going to listen to you, right? You don't know shit, type of thing. So uh, it's a fast-paced world, and the advantage of being where you're at is that you'll see a lot of things very quickly, and you'll learn and get more experience, 20 times faster than someone at PTP who, yeah, and yeah, and the thing is that the faster that you learn, and the faster that you become capable of handling these projects on your own, the way that I kind of work is my intention is to, kind of sell you to clients, right? Where we get a project that comes in, and we say, yeah, Tube can do it by himself, right? No problem. Like I'm not going to stand in between you and the client, right? So if you can handle the project and do the work, then we bill you for as much money as we can get, and you get the money, right? Like I'm not going to take it. So, I'm not trying to build a farm of slaves here. What I'm trying to do is build a farm of, highly competent consultants to do work. And then, that you benefit from that because, we'll bill you for as much as we can at, rates in the US. So, like this frac work or whatever, if you were ready to handle that project on your own or whatever, maybe we could bill you for, you know, $100 or $150 an hour or whatever, right? And that way everyone wins, right? I win because, we've got work going on and it's less stuff for me to do, and you win because you get paid a hell of a lot more money than you would just on basic salary, right? But that's something that will come with time because it's going to take a while to get up to speed. I mean, it's taken me 20 years to get where I'm at. Uh, and I learned pretty quickly. So it's going to take years to get there, but we've got so much work coming that, you know, you'll get the experience quickly. So, and the other thing that's happening, interestingly enough, too, is that with Diamondback, they've had some problems here recently where their reservoir engineers have been quitting. So they just lost 3 reservoir engineers here the last month. Um, so since I've got like a long-term consulting agreement with them, I'm sort of reaching out and kind of asking like, hey, if you're low on staff and you need some help, we're here for you. So we may have some, rate transient analysis, reservoir modeling stuff coming down the pipeline here pretty quickly as well. So yeah. So we did a study on the effects, like quantifying, just like you asked earlier, right? We did a study on how much depth shifting and normalizing affects the answers of logs. Like how important is that step to processing data? So they had a public data set that they worked with, and they put together slides, with all the work that they did. So, taking data that was not depth shifted and then depth shifting it, comparing the answers for both sort of pipelines. And they were able to make some pretty powerful conclusions and communicate that to the audience, like, hey, your porosity computations could be off by like 25% if you don't depth shift your data. So you need to do that. And this is what happens generally, right? Is that people get large data repositories, they don't do the processing or conditioning, they just dump it into a model and start mapping, the geologists, and then they don't understand that they should not do that, that it's necessary for a petrophysicist to go through that data and to carefully depth shift, normalize, edit, etc. So you could ask them, they've got a PowerPoint that they showed, they can send that to you. Yeah, see if they've got, I don't know where that thing is, so they'll have a copy of it. All right, we'll talk to you tomorrow then, I guess. Get some sleep. All right, bye-bye. Yeah.